My name is Norbert Krupp. I'm working as a staff scientist at the Max Planck Institute for Solar System Research in Göttingen, Germany. And I'm related to JUICE right from the beginning. I started as one of the members of the study team, and I'm now one of the interdisciplinary scientists of the mission, and I'm also co-eye on one of the instruments on board, which is the PEP, the Particle Environment Package, which is one of the instruments on board JUICE. JUICE is unique in various directions. So, first of all, it's a mission which is relatively complete in terms of instrumentation on board. So we can cover all the science themes which the study team has put together in this so-called science matrix. But it's also unique in a sense that it will be the first mission ever to go into orbit around a moon of an outer planet, which is the moon Ganymede. And this has not been done before, so it will be the first of this kind of a mission in orbit around the moon, and will investigate with all the instrumentation on board all aspects of science. We will arrive at the Jovian system together with a NASA spacecraft called Europa Clipper. So we will have also the opportunity to have the same 2-point measurements originally planned in the original Laplace proposal. And this is where we go back to the very beginning of the proposal of such a mission, that we want to have multiple point measurements with 2 different spacecraft in the beginning. Then we had only 1 at the end, but now we have 2 missions at the same time, and we will be able to do these science, synergistic science, 2-point measurements, looking at the aurora while being on this field line, connecting these aurora with your location you are on your spacecraft. And all these topics could not be done before, but now with JUICE and Clipper at the same time in the system, we will be able to do unprecedented science at Jupiter.
I'm Michelle Doherty. I'm a professor of planetary physics at Imperial College in London. I'm also head of department at the moment. And on JUICE, I'm the magnetometer principal investigator. And of course, I think it's the most important instrument on the spacecraft. But what it does is it measures the magnetic field in the vicinity of the spacecraft. We need to get the instrument as far away from the spacecraft as we can, so that the magnetic field we measure is due to the environment and not due to the spacecraft. We've got the instrument on this very long boom, consists of 3 different sensors, one of them halfway down the boom and then 2 right at the end of the boom. And we will measure the magnetic field of the entire Jupiter system. So we'll measure the magnetic field of Jupiter, we'll measure the field when we fly past Europa and Callisto. But the most important focus of JUICE is on Ganymede, because we're going to go into orbit around Ganymede. And that's where I lose sleep, because what we want to do at Ganymede is quite scary, in the sense that the smallest signals we're trying to measure are the magnetic field that's generated by electrical currents that are flowing in the liquid water ocean at Ganymede. And the signals are very small. But in addition to that, there are all these other things going on as well. So there's the magnetic field of Jupiter that's changing all the time. There's the internal magnetic field of Ganymede. Ganymede's the only moon in the solar system that's got its own internal field. Then you've got all these plasma currents in the vicinity of Ganymede. You've got Ganymede, because it has a magnetic field, it generates its own magnetosphere inside Jupiter's. And then on top of that, we're trying to measure these small induction currents. We can do it, but it's going to take time. And I think for me, the important thing that we all need to keep in mind is we shouldn't expect we're going to solve the ocean characteristics when we first get to Ganymede. We're only going to be able to do it right at the end, once we've built up all the information and all the knowledge that we get from all the other flybys. So it's keeping people's excitement at bay, in a sense. And that's difficult to do. I'm going to find it hard to wait that long.
I am Jan-Erik Wahlund. I am the PI of the Radium Plasma Wave Investigation, RPWI, and I come from Uppsala in Sweden and belong to the Swedish Institute of Space Physics. We will address quite a lot of different science tasks, but one of the main ones is the subsurface oceans of the icy moons. Because it's not only a magnetic signal, it's also electric signals, and we will map the currents that possibly exist within the oceans underneath the ice. We will also take a look at the thickness of the ices by using radio waves that go down to the ocean and then reflected up again. It's several different sensors radium plasma wave investigation have, because we have radio waves which we measure with 3 antenna, so we can always see where from the radio waves come, and Jupiter is the strongest radio wave emission planet in the solar system. And then we have measurements of electric fields. So we will measure the energy processes, how energy is transferred from the rotating Jupiter magnetosphere to these icy moons, and how they interact possibly with the surface. And also the moons have a kind of a thin atmosphere, and there's a lot of energy coming, and it's bombarding, and it becomes ionized. There is charged species coming, and those we will measure quite well. And then there is waves and coupling to the Jupiter itself along magnetic field lines going down to these moons, and that will be interesting to see and study.
My name is Patricia Gonçalves. I am a researcher at LIP, which is the Portuguese laboratory that does research in high energy physics and in its applications. And I'm also a teacher at university. And from the point of view of the JUICE mission, I've been participating in the development of the RADEM instrument since 2014. RADEM is a radiation monitor that will measure charged particles in the way to Jupiter and in Jupiter. Radiation is just the transportation of energy through space, and this is what charged particles do. They carry their kinetic energy in their mass to space, and that's why we call it radiation. These charged particles can be hazardous to the mission and to the other instruments, and can affect the instruments and the systems of the spacecraft. And so it's important to have a radiation monitor on board so that we can measure what is the environment that JUICE is crossing, and also to take measures to close, for example, some other instruments, to shut them down so that they don't have any problems. On the other hand, RADEM is a very special radiation monitor because it's what we call a type 4 radiation monitor, since it will measure spectra of protons, electrons, and ions. Spectra just measure the energies as a function of their fluxes. So we will be able also to make scientific measurements with it, along with the housekeeping function that it's its initial function.
My name is Stas Barabas. I'm professor of experimental space plasma physics at the Swedish Institute of Space Physics. I am a principal investigator for the particle environment package for the JUICE mission. Jupiter builds up the largest magnetosphere in the solar system, and this bubble in the space plasma, which we call solar wind, is filled by another plasma originating mostly from Io. And the fast rotation of Jupiter sets up a rotation of the plasma, and this plasma interacts with the Galilean satellites. How this very complicated system works and how the magnetospheric plasma interacts with the moons are the main objectives of our experiment. But this is not the full story. We also have a dedicated sensor which will investigate the very tenuous atmospheres of Ganymede, Callista, and Europa in order to understand what they consist of, how they evolve, and how they behave. So what is the physics behind them? I really want to study plumes from Europa. It's sudden eruptions of the gas coming out probably from subsurface ocean which exists there. If we are very lucky, we may even fly through one of them, and it will give us a chance to access to original material coming out from the ocean. So I don't know, maybe we will see even some signatures which will indicate an existence of life there. And my second favorite subject is to understand how Callista interacts with the magnetospheric plasma. Callista looks very inert. It looks like the moon or similar to the moon, but it's a very mysterious body, and particularly interesting for space plasma physics.